Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Science at the College of DuPage in Glen Ellyn, Illinois. And this video today takes a look at Day 13 of Advent of Code 2020 festivities. And as always, I am writing my code in my new favorite language, Python. So part 1, here's the code for part 1. And part 1 is basically looking at this data set here, or this big data set. This is just the sample data set, and this is the real data set. And your mileage may vary. You might have a different data set. But anyway, so what happens is you have these buses, and they're all going off at different times. And the question is, which bus will be the first bus whenever you get to the station? Which will be the first bus to come that you can take you to the airport? And so they just make it, because because all you would have to do is guess 3 or 4 times, they made it a little more complicated. So you have to figure out how long did you wait, multiply that by the bus number itself. So that's what made things a little more complicated here, rather than just figure out, I don't even know, which bus or which time or whatever. Just multiply the two together, just so it doesn't make it easy for you guys to quote unquote cheat. Me too. And so I read the file in line by line. And so the first line is the number that I'm starting with. That's the timestamp that I'm starting with. And everything else goes into this using this fancy little function here that creates a list that kicks out all the x's. We'll need the x's for part 2. But for part 1, we don't have to get rid of it, so we don't need them, so we can get rid of it. And so all that would be left would be the numbers. And all I have to do is, starting with that starting time, just go through and just say, hey, at this time, do any of you guys mod out to 0? Because 931 mod 7 is 0, and 936 mod 13 is 0, and so forth and so on. And all it needs is 1. The first one wins. And for whatever reason, we're told that there's not more than 1, but it doesn't matter. Well, I guess it would matter for the computation. It wouldn't matter for the in real life, but it would if like, oh, there's 2 buses. That's even better. But it matters for the solution itself. But once I find a number that mods out closest to the original starting number, figure out the time I've been waiting since I got there, and that's the start time minus the time that, I'm sorry, the start time. Maybe start isn't the best way to timing this. It's just time, the time in which I found my solution minus the original time, the start time, and multiply that by the bus that I found that happens to be the one that mods out. And just keep going, 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 going. And when I do that, I get my answer of 2947, which matches up with what you see there. So I'm fairly confident that this code will work for everybody. As you guys have been more than good at telling me when things don't, please continue to tell me if your code doesn't match up or your data set doesn't match up with mine, because I can only deal with the data sets I'm given. So fair enough. Part 1 is complete. Part 2 is a lot more interesting. So let's take a look at it. Part 2, again, is a lot more interesting. You are adding offsets to timestamps. You're modulating, using modulus operators to try to figure out, like this, like if this bus is, using the data set. Where's the data set? Up here. And so this is the data set here tells me that timestamps at timestamp 7 or multiple of 7, then there will be a 7 train that comes in, and then multiple of 13 plus 1, there will, so like or time plus 1, there'll be a bus that comes in 13. And then these x's are now interesting, because now it says 59 comes in at t plus 4, and 31 comes in at t plus 6, and 19 comes in at t plus 7. And so, like they are showing here, this is the example here. If I take this data set, let me just show you how cool this code is here right now. And so I don't need to change the first part of this. We don't need that for part 2 at all. But if I put this data in and I run this, you can see that I have my code here. I'll describe it in a second here. You'll see that my number matches up with the expected answer, 106.8781. And so you would think, oh, I have a solution. I'm pretty happy with this. And so what am I doing here is I'm saying that I'm opening the file, I'm creating buses. This time around, I'm creating a list of lists. And so, and what I'm doing here is taking, for every integer as I go across this, I'm taking the 7, and then the offset would be 0 because that's 0 from, basically, which element number is it? I don't know if I can, no, maybe not, no. Again, there might be better ways to do this, but I've spent way too much time on this already. So anyway, and it just goes ahead, says if it's an x, if it's an x, don't append anything, but if it isn't, then go ahead and worry about it. So let me just show you what the buses looks like. And so you will see here, oops, let me make this a little more readable here. So you can see 7, 0, 13, 1, 15, 59, 4, 31, 6, 19, 7. That's exactly what we talked about. The bus ID number and then t plus how much, t plus dx or offset. You know, so the 7 has a 0, the 13 is 1, 59 is 4, the 31 is 6, and the 19 is 7. And you're like, okay, cool, fair enough. And so that brings all the data in. And then I sort it because I do have to go low to high. At least I believe I do. I haven't tried it, and I'm talking through my code right now. And so I still believe I need to sort this because you need to go from low to high as you're counting the values up to make sure. Well, maybe not for this part because I'm adding by 1 every time. But for later on, it's going to become, I think, more vitally important that we start from the smaller numbers and work our way up so we don't lose factors along the way or multiples along the way. So all I'm doing then is I'm using this buses array now, or the list of lists, and I'm saying here, I'm just saying for the range, for as many numbers as there is in here, so in this case there's 4 of them, right? Let's see, or 5 of them. There's 5 numbers in this, yeah, 1, 2, 3, 4, 5. Go through and check to see that at whatever the value, I'm starting at time of 1, and I'm adding in the offset, because that's the important part here. I need to say, okay, what time value of this plus my offset, mod that by the actual bus number, and figure out if the bus is here or not, because the buses are always on time, right? That's just how it always goes. And the second I find a counter example, I say nope, and then I move on and I increment my value by 1. But whenever I reach a point where, you know, I find out that, or I'm sorry, I'm doing this 1 at a time or 2 at a time here. I'm checking to see that, because otherwise it would just be too darn, I guess, would it be too darn hard? But anyway, I'm just mumbling through this. But I'm saying, like, okay, first find the first 2, then find the first 3, then find the first 4, and just continue on, because it's basically trying to figure out, at least for this one, I don't think I need to, let me see, at least I don't think I need to do it. It might slow it down a little bit. Let me see what happens if I run this. Whoops. No, I guess it doesn't slow it down necessarily. I guess for this solution, it doesn't matter whether or not I have worried about how many elements I'm doing things at 1 at a time. So this again is the naive solution. So like if you look at these other data sets, they were so nice to give us these other data sets. And so I can continue on and test my data out, save this and run this, and you can see there's my answer, 1 point whatever. But this is where this algorithm breaks down. If I had an infinite amount of time, I could solve this. And you can see that it is solving it. It is getting there. The algorithm is sound, except for the fact that it is completely inefficient for what it needs to do. And so I don't recall how long this will take, but this is, what is it, 1.2 billion? And this is only a drop in the bucket, or this number here, the number you get for the true answer, or at least the number I get, which is 526 trillion, which would take absolutely forever and a day to solve. And so we need a better solution to make this work in very little time. And that's what this algorithm here does. If I can bring this down a little bit, I can run this, and you see with that same data set, I get the answer in a brief moment. And so now taking back my original puzzle data, bringing that in, and trying this again, how long does it take me? Almost the same amount of time to get my answer, which is 526. And what did I do? This is where things get interesting, and I can talk about this real fast for those of you who are interested. As is common with a lot of this kind of stuff here, the first everything is pretty much the same, but now I need to keep track of the least common multiples of the values coming in. And so I spent a lot of time in my head. I think I was dreaming about this stuff because I did not have a solution when I went to bed, but I woke up and had one in a couple minutes. Just that subconscious was working this thing out while I was sleeping. And so this is just a function to get me the least common multiple of two values, or a series of values in a list, which is pretty cool. I did steal this from Stack Overflow, but I modified it for what I needed for this. I get my buses, I sort my buses. It's the same code as before. And now you can see maybe this is a little bit different. And so what happens is I'm this time, instead of just taking everything all together, I'm trying to solve for the first two values, the smallest two values in the buses, trying to figure out where they match up for the first time. For this one, let me print buses and then you can see what I'm talking about here. Okay, you can see 13, 0, 17, and so forth and so on. And so what I'm doing is, the first time through, I'm starting with a value of 0, and I'm just naive. I'm like, I don't know where the next, or where the first matchup is going to be between the 13 and the 17. And so, like, if I have something here, I could print, just to show as things are coming together here, I can print value. Oops, I didn't mean to put it there. Hold on, let me know one second. I meant to put it in the case where this comes true. And you can see where all the, so there's 1, 2, 3, 4, however many. You can see as we go ahead and say, oh, this is where we resolve the first two. This is the number that works out for this. 143 is the number that works out for 13. It's divisible by 13, 143, and it's divisible by 17 when I add 61 to it. And so the third one comes in, and the fourth, and the fifth, and it just keeps getting bigger and bigger, and my add to value changes. It's no longer 1. That's the important part here. That was the tricky part, because in this part here, I'm like, what is the offset? What is the number that I'm going to be adding? Because 1 is way too slow. And so what we do is we figure out the original offset between the two. In this case, it's 143. And so now I know the offset. It's always going to be 143 offset from everything else, which is pretty cool. And so now what happens is I run the same kind of code, but now in my add to, I find the first one, and now everything that has to go on from now on is the least common multiple. So it's 143, but the least common multiple, I don't know what the least common multiple of 13 and 17, just 13 times 17. As I'm going, instead of adding 1, I'm going to add 13 times 17 to it every single time. And so I'm already speeding up the process 200 times, or however 200 something times. And so now it comes around and goes, oh, I found 2, let's find 3. And it finds the third value, adding 200 at a time, and it comes up something like this at 1469, and it goes, yep, that works out for the first 3. And now I know that's, everything's going to be an offset of that, but my add to value is going to be the least common multiple of all 3 of those. And goodness, it just gets huger and huger. And we just continue on cycling through as we go and just making this add to value larger and larger and larger. And you can see that you end up with the correct answer, because the least common multiple tells me how much I should add each time instead of 1, and it's a very smart way to get me to the solution here. And so this should work out for everybody. I'm pretty confident, again, that this should work out for everybody. Let's see if can I get this whole thing in the shot. There we go. And so that pretty much covers it. I had a lot of fun, if fun is frustration, but puzzle fun, trying to figure out how to do this problem. And I'm glad I could show it to you guys. So it's one of those things where in 10 minutes or so, like, how do I condense without spending hours trying to figure out how to edit this thing? How do I get this in a way that you guys can see it and work with it And if you care to understand it, try to as well. As always, swardb@cod.edu is a great way to get a hold of me if you have questions or comments, or if you know a better way to do this, because I would love to know a better way, if there is a better way, even faster way than what I've got. And you can comment below as always, and like and subscribe. For those of you listening anyway, thanks as always. This is starting to get hard. It's starting to get hard, so I don't know how much longer I'll be able to solve these by the next morning, but I'll keep posting these as I do. And as always, thanks everybody. Have a great day.